everyone. I welcome all of you to the fourth session of VSSP 2022. So VSSP is Virtual Student Seminar Program. You can say it is an online version of the student seminar conducted at MTTS campus. Today we have one speaker and we have Ilancharan Subramaniam as our chairperson. He is a PhD scholar at IIT Madras. So I like to invite Ilancharan sir for the further talk. Over to you, Ilancharan sir.
Good evening. Happy to chair this session. So today's session is presented by Ekta, and her topic is on Cantor's intersection theorem. I'm looking forward to Ekta's presentation, and people can ask that whenever they have doubts, please raise your hand, and you can ask your questions at the end as well. Over to Ekta.
Hi, my name is Ekta Keswani and I am in BSc Mathematics third year. Attended level O of MTTS. So my topic is Cantor's intersection theorem. And before I start with the statement and the proof, let me define what a complete metric space is. So a metric space XD is said to be complete if every Cauchy sequence in X is convergent in X. So if I take any Cauchy sequence in that space, it should be convergent in that space itself. So this is what a complete metric space is. Okay, so the statement. Now let XD be a complete metric space. Let Fn's, where n is in set of naturals, be non-empty closed subsets of X such that Fn plus 1 is a subset of Fn for every n in n, and diameter of Fn converges to 0. Then the intersection of all such Fn's where n is in n is singleton. So firstly, the subsets are nested and the diameter, it is converging to 0. Then the intersection is single. That means it has exactly one element in it. Now, what will happen if I drop the condition as closeness? So suppose the set I take, they are nested and the diameter converges to 0, but my sets are not closed. So do you think still the statement will hold? The intersections would be singleton. If you are not convinced, then you may give an example. So my question is, if I drop the closeness condition, will the statement be true or not?
I don't think this is true.
You have an example in mind.
I was thinking of taking R with the usual metric and looking at something like 0, 1 by n.
Yeah. So I think, okay. So do you think the nestedness holds here in 0, 1 by n?
So if we keep 0 open, if we keep both sides open, I think it does.
Yeah, and the second condition also holds.
Yes.
So the can you tell what is the intersection of all such Fn's?
It's empty, right?
Right. So that's true. So I think the closeness part is important. Now the next thing is, what if I drop the condition, this second condition, diameter of Fn converges to 0? So as the last person said, the example for 0, 1 by n. This is also one of the example which works. Then, so if I keep the non-emptiness, closeness part intact and nestedness also, but I drop the condition of diameter of Fn converges to 0. So suppose the diameter converges to some other point and not 0. Will the statement still be true? If you think so, you can give, you can say that it's true, otherwise you can give a counter example.
For any natural number, we can take Fn as 0, 1, close 0, 1. Diameter will not reduce to 0. Nadu?
So what is your X and B?
R and usual distance we are taking.
So your FNs are 0, 1.
Yes, interval 0, 1. Close interval 0, 1.
Okay. Right. That works. And similarly, this also works. So you can think of other examples as well. Now moving on to the proof. So my statement says that FNs are all non-empty. So since the sets FNs are all non-empty, so for every n in a set of natural, I choose a point xn in Fn. That means x1 in F1, x2 in F2, and so on. So we have a sequence xn. Now, in the statement, it was diameter of Fn converges to 0. So by the definition of convergent sequences, let epsilon positive be given. So there exists n naught in n such that for every n greater than or equal to n naught, mod of diameter of Fn minus 0 is less than epsilon, which is nothing but diameter of Fn is less than epsilon.
I would like to pause for a second. Can you please explain what is diameter? Fn is a subset in a metric space, right?
Yes.
So
Yeah.
would you like to explain what diameter of a set is?
Yeah, sure. So diameter of set is defined as a supremum of the distances between x and y, where x and y are from the same set. So if I take any 2 points x and y from Fn, the supremum of the distances between them will be my diameter. So that is how diameter is defined in a set. Okay.
Yeah.
So yeah. So to prove that this sequence xn is Cauchy. Now, again, we use the, okay, so before that, so for every m and n greater than or equal to n naught, xm is in Fm. This part is convincing. Similarly, xn is also in Fn by our very choice of points. So now, since m is greater than or equal to n naught, Fm will be subset of Fn naught. Why? Since we in the statement it was mentioned the nestedness part. So Fm is a subset of Fn naught, and Fn is also a subset of Fn naught, which implies that Xm is in Fn naught and Xn is in Fn naught. So that implies what? That the distance between xm and xn is less than or equal to the diameter of Fn naught. Why do I say so? So because I define what diameter of Fn naught is, it is the supremum of the distances between the elements of the Fn naught. So xm is also in Fn naught and xn is also in Fn naught. So the distance between them will be less than or equal to the diameter of Fn naught. And because we said by the definition of convergent sequence, this is less than epsilon. So diameter of Fn naught is also less than epsilon. Now, so by the definition of Cauchy sequences, we proved that Xn is Cauchy. Now, so I defined what a complete metric space is. So since X is complete, which implies that the sequence Xn which is in X is convergent in X. So it converges to some point X in X. Now my claim is that intersection of all such Fn's is singleton X. Okay. Yeah. So how do we prove that X is in the intersection? So we fix some point K in a set of naturals arbitrarily, and whenever n is greater than or equal to k, the sequence xn is in Fk, which converges to X. This means that, so whenever n is greater than or equal to k, the sequence xn will be in Fn. But since Fn will be subset of Fk by the nestedness, so xn is in Fk, which converges to the same limit point X. So we have now not all the terms, but finitely many terms will be in Fk. So so we have a characterization in, like we have a characterization theorem that a point is in the closure if and only if there exists a sequence. So suppose A is a subset of the space X. So I say X is in A closure if and only if there exists a sequence of points of A such that Xn converges to X. So thereby there is a sequence Xn in Fk which converges to X. So by that characterization, this implies X is in Fk closure. Yeah. So again, using a result that the closure is equal to the set itself if and only if that set is closed. So we started in the statement, we started with non-empty closed subsets. So since Fk is closed, Fk bar, that is Fk closure, is equal to Fk. So that X is in Fk for every k in n. So why for every k in n? Since we started with any k, so it holds for every k in n. So therefore, X belongs to the intersection of all such fn's where n is in set of natural. So this part is done. Now I have to prove again my claim that the intersection of all such fn's is singleton. So we show that X is the only element in the intersection. Now, suppose there exists some Y in the intersection. So this implies for every n in n, X is in Fn and Y is in Fn. So both of them are in the same set. So the distance between X and Y will be definitely less than or equal to diameter of Fn by the definition of the diameter of a set. So, so if it is less than equal to diameter of Fn, this is actually, so for every n in n, right? So after a point also this will hold. So for every n greater than or equal to n naught, this will hold true. So I said for every n greater than or equal to n naught. Again, going back to the nestedness, Fn will be subset of Fn naught. So this implies diameter of Fn will be less than or equal to diameter of Fn naught, which is less than epsilon. As we proved by the convergent sequences, we said that diameter of Fn naught is less than epsilon. So combining this part, 0 is less than or equal to distance between X and Y, which is less than epsilon. So this implies, and further that implies that the distance between X and Y is 0. So if the distance between 2 points is 0, that implies that X has to be Y. So hence the intersection of all such fn's is singleton X, and thereby my claim. Yeah. Thank you.
Okay. Can you go to the statement once?
Yes.
So can you quickly tell, you used complete metric space at some place. Can you tell what do you mean by completeness when do you mention a metric space to be complete?
Yeah, so a complete metric space, suppose let XD be a metric space, and that XD is said to be complete if and only if, not if and only if every Cauchy sequence in that space is convergent in that space.
Okay.
Yeah.
Okay, so we'll go for questions from the audience.
Yeah.
So now it's time for the audience to ask their questions and doubts. Yes, Pranay.
Yeah, two things. While she was mentioning, hi Ekta, while you were mentioning this completeness, you said that not if and only if. Why? Is it not if and only if? I hope you can hear me.
Yeah, you're audible. Ekta, we can't hear you. Can you mute yourself, unmute again? Let's see.
Yeah, I can hear you.
Yeah, we can hear you now.
Yeah, I think it is an if and only if.
I mean, that's how it is defined, right? X is said to be a complete metric space if that's the definition of complete metric space, right?
Yeah.
Yeah. Okay. And also, could you just go back to the last slide where you prove uniqueness?
While Ekta goes to that part, I'll just mention, like, I think that's the exact reason why she took back the word if and only if, because that's the definition. So suppose if it's like a statement A is true if and only if a statement B is true, then that's a different thing. Here you're just defining what a complete metric space is.
Right. But Ellen, I mean, definitions by default are if and only if, right? I mean, so it's not like.
But if and only if, in the sense, I guess it's more of a convention for me at least. I take it that way. Both is right, and there is no necessity for if and only if there, because what is complete metric
since you're
space?
defining it, yeah,
it's just defining.
Yes.
So here you are saying the diameter of Fn is less than or equal to diameter of Fn naught. You are assuming that n is bigger than or equal to n naught here, are you?
Yeah. So for every n in n, I said this will hold. Now, if n is greater than or equal to n naught, still the statement will be true.
Oh, okay, but that you haven't mentioned here. I just wanted to point this out, that you need to mention that here, right? I mean, since n is bigger than or equal to n naught, see, above statement is for every n this holds, right?
Right.
So if you take n bigger than or equal to n naught, if you fix some n naught and then talk about n bigger than or equal to n naught, then this holds, right?
Yes, it does. Yeah, right. So I just spoke about it, but I've not mentioned here.
I mean, right. So you are using that. I mean, okay, fine. Yeah. So n is bigger than or equal to n naught implies this, and okay, right.
Yes.
Yeah.
Pranal, do you have a different question? These are the two.
No. These are the.
Okay. So I have a comment to add. So, Ekta, you mentioned in the first, second line of the uniqueness proof that that x and y belongs to Fn for every n, right?
Yes.
In particular for.
Sorry, I did not get you.
That x and y belongs to Fn for every n.
Yeah.
In particular, it holds for. Can you tell one specific natural number? Some that will be of helpful to you.
For n naught, in particular, it holds for Fn, like n naught also.
Exactly. So x and y belongs to Fn for every n. In particular, it holds for your stage n naught as well.
Yes.
So you don't have to worry about this center part. You can remove the diameter of F subscript of n and directly write.
Right.
So that you don't have to worry about n greater than or equal to n naught. This.
Yeah.
Right. Cool. Okay. So yeah. Any other questions from other people?
We got the proof again. The existence proof.
Can you come again?
The existence proof. Could you go to the existence of such an X that we proved initially, like I think the first slide of the proof.
The previous slide. Yeah.
The previous slide. So I had a question here. In the first line, you said that since the sets Fn are all non-empty, so for each n we choose a point xn in Fn.
Yeah.
So are you specifying a way in which we're choosing this, or like because Fn could have multiple points, right? They could all be infinite sets for all.
Right, I'm choosing a point, no? So that is my choice.
I see. So we can just take, there is no specific algorithm or a way in which you're just like choosing an arbitrary point.
Yeah, so for every natural number, I am choosing a point. So it is up to you. You can choose xn plus 1 in Fn. So that ways. So x2 in F1, x3 F2, that ways. That is up to you.
I see. I was thinking about the axiom of choice, honestly. That is why I was wondering if that is applied here, because choosing a point, it seems very random to me. That's the only question I had.
You choose an arbitrary point in each Fn, and such a point can be chosen because Fn are non-empty. And however arbitrary the choice is, the argument still holds. And that's the proof.
Thank you. That's my question.
Any other questions? Raise your hand or you can unmute and talk. Okay, so we'll wait for 10 seconds. If any questions, please ask. Else, we'll.
I just want to add something, Elan.
Sure.
If Chirag is still here, Chirag?
Yes.
Yes, sir. I'm here.
Yeah. So see, basically, she just wants you just want a sequence. By the very fact that diameter of Fn converges, I mean, you just want a sequence so that you want it to converge, right? I mean, so in this case, completeness does the job, but I mean, you just want a sequence, and the way you can do it is take a point in each set, each nested set. So by the very fact that diameter converges to 0, it becomes Cauchy. So you don't have to do much. I mean, it's diameter of, you're just using the fact that diameter converges to 0 there. So you just want a sequence. I mean, you ask, right? I mean, is there an algorithm as to get a point or to choose a point? So there is no algorithm, as Elan was saying. This you can take arbitrarily. Even if you do that, the sequence is bound to be Cauchy. It has to be Cauchy because of the diameter going to 0. That's all. Yeah. I don't know if this was I added to your confusion or.
No, thanks for the clarification, sir. That does help.
Yeah. Thanks, Elan.
Yeah, thank you. Okay, so I'll end with a question and then a thanks. So in the same statement, if we don't assume that the diameter of the subset is going to 0, what can we tell about the intersection? Ekta?
Yeah, so the statement won't be true.
No. How can we modify the statement? If we don't assume that the diameter converges to 0,
Okay.
then the intersection will be, it need not be a singleton, but it will be non-empty.
If it is, the diameter is not, it doesn't converge to 0, then I think the singletons would be, I think it would be empty.
Okay. So I leave that question for you to think. And Harinder, is this a good point to stop?
Yes, sir. Thank you, sir, for joining us. And I'd like to thank you all the participants. And thank you, Ekta. So I think we can stop now.
Yeah. Thank you. Thank you all.